All right, today we're going to be going over technical session number 8. I know we've only done 1 through 4 so far. Remember, we do jump around in these a little bit to closer, so that it more closely matches with the Coursera courses that you're going to be moving through over time. So today we are going to be talking about the central processing unit. For the most part, the computing part of the brain of the computer itself. We have talked a little bit about the CPUs leading up to this point, kind of just giving us a little bit of an intro before we get started on it. On this one, you can see in the picture as we were talking, see if you look right about here and here. What is that?
The triangle that we're supposed to like match it up with.
Match up what? What does that tell us? What does that indicate?
Orientation.
Pin 1.
Oh,
So if that triangle is here, we know right there, that's pin 1. So we will know that, and it helps for orientation and things like that. So it gives us the orientation of the chip, lets us know where pin 1 is so that we know how to put it in properly into the board. Thankfully, though, to make life a little bit easier for all of us, they add these fun little notches here and here, which makes it easier to determine orientation for inserting the chip into the motherboard. All right, throughout this technical session, our objectives are to describe the various types of processors. There are going to be 2 main ones, of course, that are the players in the industry, and to articulate how to select a processor to match your system's needs. Identify the CPU as the central processing unit and explain its purpose and requirements to keep it functioning. Also, be able to choose the appropriate cooling method you're going to need for your system. There are a few to choose from. Like there are some that actually use liquid and a radiator, like in your car, to cool their systems. There are systems that are completely submerged in liquid and use that as the cooling system. So yeah, it's almost like a fish tank with a computer in it. So there are cooling systems that operate like that. We're going to work on naming the steps to replacing and installing a processor in our systems, as well as identifying the common pitfalls you'll come across while doing so. Also, giving certain symptoms, we should be able to identify common CPU problems and describe how to solve them. We're also going to be taking a look at the internal architecture of modern processors and how they work, how they allocate memory and things like that. So, behavior, skills, and mindsets we want to keep in mind. Growth mindset. It is a continual learning process. Anybody can learn. And what do we often say? If you want to be successful in IT, be interested in IT. If you're interested in it, you'll make the time to learn about it. We always make time for the things we are interested in. So we want to maintain that growth mindset, continue to develop, continue to grow and learn. And adaptability. The industry is always changing. We need to learn to adapt and maneuver and change our perspectives as we go. We cannot change the winds, but we can adjust our sails, so to speak. So, first, the types and characteristics of central processing units. As we have seen in previous ones, they are installed directly onto the motherboard to provide computing power and processing power for the motherboard themselves. There are 2 major brands that we have discussed in prior technical sessions. You have the Intel and the AMD. Each of these manufacturers operate with different types of chips and characteristics, and some of them are physical, some of them are in the internal architecture themselves. As we talked about yesterday, how would we identify the difference between these 2 chips physically? If we were just looking at them, they were laid out on a table, we couldn't see the name on the back of them. How would we know the difference between an AMD and an Intel? Let me give somebody a call out here. Renzi, could you please tell us?
Sorry, I'm in the middle of something. Can I?
Yep, we can go. You can go later.
Okay, thanks.
All right, Justin.
You'll be able to tell the difference between the AMD and the Intel, because the Intel is more smooth and one has the pins you can notice PC on.
There we go. One has pins, one is smooth. So very good. Thank you, Justin. So that would be one physical characteristic that would maintain the difference between the two of those. First up, Intel. You do need to kind of know the naming styles for these chips, at least up to about 4 years ago. They are desktop and laptop processors for Intel typically. They're sold under different names like Core, Pentium, Celeron, things like that. You will need to know that when somebody's mentioning these naming types, that immediately guides you towards Intel, especially for the exam itself. They are low power, portable, smartphone chips that they have. They're called Atoms. Their high-end server chips are called Xenon. So the names that just need to desktop, you have Core, Pentium, Celeron. Phones, they have Atoms, and for big servers, Xenon. Some of the laptops have the Centrino technology, which interconnects the processors, the chipsets, and the wireless adapters into one unit to kind of improve performance, as we were talking about yesterday. Over time, they're trying to integrate more and more and more into the CPU, because the closer that stuff is physically to the center of the processor, the faster that processor can react to information from it. And so as we are able, and this technology gets smaller and smaller, we want to incorporate it more into the CPU. First step usually is incorporating it into the motherboard itself, and then eventually into the CPU over time. So here are some, here's basically the evolution and some of the main names of the Intel CPUs. You do not need to memorize all of these. This mostly have an idea as to how they do their naming, but also how they've grown over time. So you can kind of see, from 1971, they had a 4-bit, it's 4-bit processor, that small. So that's 4 ones or zeros. So, and then they moved up to a 16-bit, 32-bit, and now they're up 3264. And now they're basically fully evolving into just straight 64-bit processors as we have evolved. So you have you can see it where they just had the 4004, the 8086, and then they moved into the Pentiums, the cores, and now they're into the i3, i5, i7s. Questions so far on Intel?
The 2007 chip where it says Core 2,
Mm-hmm.
what does that particularly mean? Does that have anything to do with the power or no?
No, well, it's kind of like from prior chips, it's like 2 CPUs, 2 cores, 2 processors in one. So they've essentially, because remember we were talking about Moore's law, how things get twice as fast and half as expensive every 18 months. So we were starting to run into roadblocks on that, where we could only fit so much into a single processor. So they started fitting multiple processors into a central processing unit. So that unit becomes a housing for multiple cores, so to speak. And they do interesting like programming magic as well to make these cores. So if you have 2 cores, if you use the multi-threading technology, you can make the computer think there is 4. So you have 2, but the computer thinks there are 4. But we'll get into that here in just a moment. Any other questions? That was a good one, Mark. I like that.
What about the Intel Core i3s, i5s, and i7?
That I believe, is more to the generations, the i3, 5, 7, 9, and then they will have varying cores within that, if I remember that correctly. So it's like iteration 3, iteration 5. So it's like the generations of the chips in that grouping. All right. AMD, competitor to Intel, also called Advanced Micro Devices. They have been popular in the gaming markets due to their GPUs and the fact that they are significantly less expensive than Intel's. Intel, historically speaking, was far more expensive chip. You didn't get all the fun, fancy performance out of the AMDs that you did out of the Intels, but you got a lot more bang for your buck with regards to the power of the processors you could buy. Now, AMD has been lately making very big strides and are now able to do the multi-threading technology. They were not able to do that until 2009, I believe. That was something that Intel had far over and above the Intel chips. They didn't have that multi-threading technology. AMD is now capable of that and are really making a name for themselves in the gaming markets for chips, but they still are operating at a much lower cost than trying to buy an Intel chip on top of that. Unfortunately, in today's market, both are extremely expensive due to shortages going on with supply chains and stuff like that. But pre-2020, that was the rules for the microchips. All right. Now, the ports for the AMD, as we talked about yesterday, visually different. You have the little sockets where the pins will go down into the motherboard chip with, as opposed to Intel, where they have the pins coming up out of the board and then the chip sits on top of those pins. So that is the physical difference that we were talking about. The families of chips that they have in the AMD arena are the FX, the Phantom, Phenom, Athlon, Sempron for desktop, and the Athlon, Turion, V-Series, Phenom, Sempron for laptops. Again, know the families, stuff like that. I know we're getting into the Ryzens now. It's a newer one, but those were not in wide use when the exam was written. So again, real life versus the exam. The exam stops at Sempron. Questions so far?
So I got a quick question for the Intel.
Mhm.
So, I have an Intel i5 processor, CPU, whatever. Question is i7 faster than an i5? Is I've been wondering for a long time now.
Okay, so it's quick and dirty answer is yes. The actual answer gets more into it depends on the chip in those families. So if you buy the highest level of i5 versus the lowest level of i7, which is the generational, there may be performance differences where the i5 is faster. So in general, yes. But, so at a certain point, you may not even notice the difference between the two. And there might be a number of cores that you're talking about that is a difference. And if you're not setting up hypervisors, like if you start getting into the Ryzen 9s and beyond that, where they have, a ton of cores, and then they have the hyper threading on top of that, unless you're setting up hypervisors and running tons of virtual machines, you're not really going to see such a drastic difference between the one generation to the next. So that's partially how it goes. Does that make sense? It's kind of like the generations on RAM. If you get a really good DDR2 versus a DDR3. So if you have a DDR2 with low latency and the highest end for that generation, you will exceed the performance of a DDR3 at the lowest performance with, high latency. So it's a matter of, in general, yes, but can you find specific examples that violate that rule? Of course. All right, good question though. Any others? All right. So this kind of breaks down the AMD CPUs into the various segments that they have, and the value segment, which would be the economy class, which would be the lower cost. But if you're not using it for much more than running word processors or spreadsheets and things like that, this is pretty much all you need to worry about. So you don't need to buy, a really big souped up computer just to work on your spreadsheets and answer email or surf the internet. So the AMD Sempron works out pretty good. Mainstream, using for, general purposes, running a lot of applications, maybe running VPNs into your office and running, virtual desktop, stuff like that. Mainstream probably work pretty good. Digital media, if you're going to be doing streaming, things like that, or, working on CAD programs, things like that, that works out pretty good. And then you get into the gaming segment where you're trying to go for the highest processing power you could possibly find and trying to develop as many frames per second as possible, dealing with 3D graphics rendering and things like that. Questions so far? Now, you do not need to remember every one of the chips. I'll reiterate this a couple of times. You don't need to remember all the chips, but you need to be familiar with the families and the naming types. So you need to know Athlon, Sempron, and all that. That is AMD. You need to know that Pentium Core, and then the I series, i5s, i7s, i9s, that's Intel. You need to be able to identify that. So that's your specific kinds. Did you have your hand up, TK?
You answered my question.
Okay. So we need to be familiar with the families of chips. All right. Marvin went through this with us yesterday. Got to see these fun slides. All right. So we see the CPU. This graphic should be familiar from yesterday. You have your CPU, which does all the computations, complex computations for the computer. It is basically like a giant calculator, very powerful calculator. We have our clock generator, our North Bridge with our most high-speed connections needed, our RAM, our graphics cards, things like that, USB 3s, USB-Cs, stuff like that. That's going to need super fast connection to the processor. All that goes through the North Bridge. South Bridge, you got your PCI connections, the ARM board graphics controller built into the motherboard. You have the flash ROM and the BIOS connected to the South Bridge. And then you have the super input output chip that kind of helps the South Bridge communicate with the extremely slow speed technologies like a keyboard, a mouse, or things like that. That would go through the super IO. Because they're not going to be moving as fast as, say, a graphics processor, or even as fast as your PCI buses as well. Questions so far? This is just a review from yesterday. All right. Here is a look inside one of the cores. These are the pieces that would be inside it. So you've got your algorithmic logic unit, which is right here. This is where all the powerful computations are being made. That is the essentially the main processing portion of it. You have the control unit. That is essentially like your traffic cop that's saying who goes where and who's handling what. You have the registers, which is like small holding areas on the processor chip. They hold on to instructions and address the algorithmic logic unit is currently processing. So it kind of holds on to things for a little bit while the ALU is trying to process it from time to time. And then you have the internal memory cache, which is not too dissimilar from the memory cache, say for your websites, like when you're reaching out to a website. Every time you, like if you go to Google 500 times a day, it's not going to go to Google and download the entire website 500 times a day. It's going to hold that stuff in memory cache so that if you try to go to Google, it boots up an older version that it has loaded to make things run faster for you. So things that you're going to use regularly or multiple times, your cache memory will hold on to that just to make things happen a little faster for you. Same here in the CPU, you have an internal memory cache that holds on to that information for it. That's stuff that's going to be regularly needed, or if they're requesting the same information over and over and over again, they will hold that information in cache so that they can access it much quicker. Or if you're being asked to make the same computation over and over again, hold the answers to that computation in cache. That way you don't have to keep doing it. Does this make sense to everybody? We can build our own CPU now. Give you a soldering iron, silicone wafers, good to go. All right. Good. Me either. Don't worry about it. All right. So moving along a little bit further, this is kind of the components we were talking about in the last one. Oh, also the input output unit. Sorry, I forgot to mention that one. That's basically, you know, everything that's coming in and out. It manages the data coming in and out of the processor itself. So IO, or input output unit. That is the basic internal structure of the core itself, and allows you kind of an insight as to how information is shuffled around inside that core. And then the buses are the lines or connections in between those things where the information is traveling. Like if you look top down on a microchip, you've probably seen it in movies or something like that. If you look down on it, it looks like a city with a bunch of little buildings on it. And then it has the little pathways in between each thing. Those pathways are what's carrying the data and the power to the various pieces. So those are basically the roadways, but they call it the bus. All right. Registers. Sorry, let me go back. Ash was asking about the registers. They're small holding areas inside the ACL, the chip where the algorithmic logic unit is trying to make computations. Sometimes it can't hold all the information it's trying to compute. So it will push that information onto the registers. The registers will hold on to it for 5 seconds. Like, okay, you know, I figured out what, 15 times 20, 37 divided by 6, and 18 times 4. I don't have time for, the third derivative of this equation. Register, please hold that for me while I'm working on this. So the register will hold on to it. Once you've gone through what it can handle, then it'll push that piece of the equation up to the register, grab the piece that hasn't finished, bring it down, work on it a little bit, grab it, and then send it out. So the register is just kind of like a holding area, kind of like RAM for the computer. When the CPU is trying to work on something, and it uses the RAM to kind of hold on to stuff for it while it's working on other things. The register does that internally for the cores because you have varying levels of short-term storage. Does that make sense, Ash? Beautiful. All right. There we go. Things to consider when you are selecting your central processing unit. The speed, obviously, that's one of the most important factors that we all consider when we're looking for RAM and we're looking for, processing units. Like, how fast does it go? It's usually one of the first questions outside of how much does it cost. So we want to know how fast it can make those computations. And it typically is measured internally in gigahertz, and it's what clock speeds the processor itself will support. Clock speed is determined by what? What determines the clock speed on a computer? Let me grab a pen here. Chris M., what determines the clock speed?
I'm trying to think of how to word it.
Give me a hint.
You pointed to your wrist?
Yes, it did.
what determines it? I mean, it's how fast is it not how fast it processes data?
Like Alan is,
The quartz crystal.
the quartz crystal determines the clock speed of the motherboard.
Oh, okay.
So you need to know what clock speed your processor can handle from the motherboard. So that's part of what determines compatibility. Motherboard restrictions. What architecture does the CPU have? If you have a motherboard with a 32-bit architecture, you cannot put a 64-bit architecture on it unless it also is 32-bit capable. So we have to pay attention to the architecture. Memory cache, how much can it hold? The socket type that is on that chipset, will it actually fit in what we're doing? And the compatibility of the manufacturers. Multiprocessing capabilities. Is it capable of the multi-core processing, multi-threading, and dual processors? Now, CPU, if what you're trying to do, like if you're trying to set up a hypervisor where you're going to have essentially virtual desktops for other people to use, like in your office, you may have a server that all the desktops are run from that server. Everybody logs into the server, and that's where they get their operating systems from. In order to do something like that, you would need to have virtualization capabilities and also multi-core processing capabilities to be able to handle that as well, because every instance needs its own core. Also, security and the integrated graphics. Are you going to rely on those integrated graphics, or are you going to have to make yet another upgrade and get into a graphics card? Questions so far? Who's the control? Who's essentially the traffic cop for the this core itself? Who manages where the information goes and who gets what?
The AMD.
The what?
AMD.
Inside the core. AMD would be the chip manufacturer. So
Central unit.
close. The what?
Control, is it control unit or central
That
unit?
absolutely is correct. TK, control unit. Very good. What makes all the fancy calculations?
The arithmetic and logic unit.
Yes. Yes. And Janina also got that in chat. The ALU, arithmetic logic unit. Now, if I'm making computations over and over and over again, so I don't have to keep doing the same thing multiple times, where would I store that information so that it's quickly accessible? So I don't have to make those calculations again. They're already done. I just store them somewhere. So where would I look for that?
The register.
Cache.
Cache. Now, lastly, if I'm making a bunch of computations, but it's too big for me to hold, I need them to hold something temporarily until I can get to it and work on it. Where does that get held? Registers. All this is internal workings inside a core on a processor. Very good. All right. Clock speed. We already talked about this yesterday. There is the quartz crystal that sets the clock speed for the computer. And the CPU's clock speed is the maximum speed that it can handle, not the speed at which it must run. So it can run lower than that, but typically that would the speed it gives you is the maximum it can handle. If we want to exceed that, what do we call that?
Overclocking.
Overclocking. There we go. So if we want to, essentially redline it, run it a little over what it's supposed to, we can overclock it and get a little more performance out of it. But what's the drawbacks of that?
Heating and power.
Heat. So it generates more heat. So you're right there.
It will limit the lifespan of your unit.
There you go. And it will diminish the lifespan of your unit. So it generates more heat. So you're going to need to upgrade your cooling if you're going to do that for any significant time. And it's going to decrease the lifespan of your CPU. If you're only planning on having it for 6 months, have a party. If you want to have this thing for about 10 years, like a car, you might want to treat it a little better. You might not want to dog it out all the time. Don't punch the gas every time you come off the starting line, or, you know, when the light turns green, you want to take it a little easy on it. It'll last a little longer. But if you really need to get more performance out of it, you can amp it up by overclocking it. All right.
Quick question.
Okay. What's up?
So I have a gaming laptop. So is it overclocking if I use the Nitro Sense feature, which is like the RPMs, like I increase it from like 2,300 to like 6,200. Is that considered like overclocking my CPU? Like,
You might have to show me that because I have not actually worked with that.
oh, okay.
So you might actually have to show me that. Let's when we get done with the technical session, I'd like to see it. But
Gotcha.
that's an interesting thing. I've never seen the Nitro be used for it, and I can't determine if it's overclocking right off the bat, so I don't want to give you bad info. But that's definitely one we're going to revisit. All right, CPU architecture. This will let you know what type of operating system you can use. So you have 32-bit processors. They're also known as x86 processors. They can handle 32-bit operating systems. Why they're named x86, I don't know. I think somebody mentioned the year that they got to the 32-bit was 1986. Not sure. That may be what it is. We made it a little easier. When you get 64-bit processors, they're known as x64 processors. Yes, Jimmy.
What exactly is a bit, like a 32-bit?
It's how much it can process at any given time.
Okay.
It's
Do you know what
processing
the
capabilities.
Do you know what it's short for? Like the word?
Bit?
Yeah. It's just
Bit
bit.
is like a 1 or a 0.
Okay. Okay.
So
Oh,
your
okay.
bits,
Okay.
bytes, nibbles.
Okay. Oh, okay.
So a bit is a 1 or a 0.
Like from yesterday. Okay, I got you.
Yep. So yeah. So 64-bit processors, also known as x64. They require 64-bit operating system, but can still handle 32s, 32-bit applications, but by simulating them like in a virtual machine, a 32-bit processing. So it's essentially kind of tricking it or dumbing it down so that it's able to do that. They do have hybrids that can do both. And AMD produced the first one of those, so which is the AMD 64. But typically they are one or the other, but you can kind of trick it to work with a 32. And 32s cannot be tricked to operate on 64s. Just, you know, it is a one-way street. They can go backwards, they can't go forward. So you can't get a 32-bit to run 64-bit applications or operating systems, but you can get 64 bits to run 32-bit operating systems and applications. Questions so far?
Did you explain why the 64-bit processors can only handle the 32-bit applications?
No, the 64-bit can handle 64-bit applications, but they can also be made to handle 32-bit. So they can handle something that's slower than they are. You just can't have a 32-bit handling something faster than it is. Does that make sense?
I got you.
Okay. So let me go ahead, pause it right here for a moment. Okay, moving along. Multi-threading. Beautiful technology. It is essentially means, the aspect of multi-threading means that each core in your processor can process 2 threads at the same time. Typically, they could only do 1. They figured out a way to make it so that they could actually do 2 at the same time. So it makes one CPU act like it is 2 CPUs. So beautiful technology. In fact, if you go in and look at the cores on your machine, you might sit there and think like, oh, I have a quad core, but then you go and you look it up and it shows 8 cores. That's because of the multi-threading technology. It is not a glitch. It is not an error. It is showing you, because the system, the way it's processing information, it's acting as though it has 8 cores when you only have 4 physically. So it is a wonderful thing. It allows you to do much more complex computations. It allows you to run multiple virtual environments if that is something you wish to do. And it allows for much greater functionality. Intel calls their version of multi-threading hyper-threading. They were the first to come up with this of the big two and implement it in their normal technologies. AMD, apparently it was 2017. I was wrong. It was not 2009. 2017 started to utilize actual true multiprocessing. Go. And here is, if we took the covering off of that CPU that we would, we were seeing earlier, this is basically what it would look like.
Hey,
And
Kelly.
so, yes. Can't hear you. Can you go ahead and type it in chat?
Can we go?
I think she wants to go back one.
Go back one. Okay, let's go back one. There we go. So moving on, here is a look inside of a CPU. If we pulled off the cover from like the chip we had at the beginning, you can see right here, this is a 4-core processor. You got 1, 2, well, you guys don't see my mouse. Let me annotate here. So you got, 1, 2, 3, and 4. Those are your 4 cores. Can anybody tell me what this looks like right here? What does this look like over here? You don't necessarily need to know what the item is, but on top there, what does that look like?
For heating?
Do what?
Heating?
It is a heat sink. So even inside of a central processing unit, they actually utilize heat sinks on the internal chips. It's very tiny, but it is there. So today, it is very, very common. I think almost all CPUs have multi-core processors within them. Yes, Evan.
Do heat sinks vary in size?
Absolutely. And functionality. Like this one right here is probably about, say about 1/2 inch long and probably just a few centimeters tall. But it's enough to disperse the energy or the heat buildup from the chip underneath it. Then you have the ones like on your central processing unit, which will be the full diameter of the chip itself, and then maybe 1 inch, 1.5 inches tall, each of the blades on that heat sink to help draw the heat away and so it can be easily dispersed. Questions so far? All right, so within the chip, we have, so this previous picture that we have, and go ahead and erase my drawings here. So we have 4 CPUs in this processor, right? And then if we look back to that previous slide, oh, wrong back button. There we go. So if you look back to this one, this is inside a single CPU. And then this is a processor, and this is an individual CPU. So that previous picture is all inside this one little box. And then they have 4 of those inside of a quad core processor. Now, in order to kind of help manage the memory and the repetitive computations they have to do, they have different levels of cache memory, which is something that you're storing that you don't want to continue to do those computations. You want to keep it there so that you can easily grab it and use it again, and it allows for greater speed. So within processors, they actually have 3 levels of cache memory. And unfortunately, yes, you do need to know the 3 levels of cache memory. So you would have in here, first you would have level 1 cache memory. It is the smallest, most expensive, and it is built right on, change the color here, into each processor. So each CPU has a level 1 cache built right into it. So it's the most expensive, it's the smallest, but it is absolutely the fastest because it's right there integrated into that CPU, available, ready to go, the shortest connection time, and operates really quickly, but it's very expensive. It's not something you can upgrade, but it's built onto the chip itself, into each individual CPU. Next, you have the level 2 cache, which each CPU has just outside of it. It's not as expensive. Level what?
Level 2 cache is right outside of the
CPU, just on the outside. Level 1 is built into the CPU. Level 2 is just outside the CPU. I believe this is it right here. I gotta change my color again because my palette changed. So right here, I believe these are the level 2 caches on the chip itself. So you have level 2 cache. Each CPU has its own level 2 and it's right outside. It is less expensive than level 1, but it's not quite as fast as level 1, but there is more storage available. So that is level 2 cache. Everyone got that? All right, next we have level 3. Change my color back. So level 3. Still inside the CPU or inside the processing unit, but it is shared by all of the processors involved. So you have 4 cores. The level 3 cache is shared by all 4 cores. Of the 3, it is the least expensive, but also offers the most storage, and it is the slowest of the 3. And this is all held within the processor itself.
Say that one more time.
Which part? Like start at level 1?
No, level 3, please.
Level 3. Okay, level 3 is outside of the CPUs. So in this case, we have 4 CPUs. We got 1, 2, 3, 4. So we have our 4 CPUs, right? Level 3 would be outside of the CPUs and shared among all 4 of the CPUs in this quad core processor. So quick refresh. Level 1, most expensive, fastest, and built on top of each one of these CPUs. So in this quad core processor, you would have 4 level 1s built onto each of those CPUs, fastest, most expensive, but the least amount of storage. Level 2, just outside the CPU. Each CPU has its own level 2 cache, and it's a chip just outside. It is less expensive than level 1. It's also slower, but there's more storage than is capable on the level 1. And then finally, level 3 cache is outside of the 4 CPUs, still inside that processor, the whole processor quad core, and it is shared among all 4 of the cores in a quad core. If you had 8 cores, it would be shared among all 8. But in this example, there are 4 cores, so that level 3 is shared among all the cores. It is the least expensive of the 3, offers the most storage. However, it is also the slowest of the 3. I did see at least 2 questions like on the level 1 through 3 cache on the 1001. So bear that in mind. Any questions so far? Yes, Renzi.
I thought you said that L1 was the fastest, but did you say that L3 was? I feel like I'm confused about L1 and L3 being, which one's the fastest?
Okay, L1, with regards to computers, always try to bear in mind, distance from where you're trying to be makes a difference, a huge difference. So the L1 is built right on top of that central processing unit right here. So it's built on top of it. So it's gonna be hands down the fastest.
Okay.
It's gonna be the most expensive to integrate.
Mhm.
And it has the least amount of storage.
Okay.
The L3 is shared by all 4 of these processors, has the most amount of storage, but it is the slowest, but also the least expensive. So it's your distance from where you're trying to make those computations determines the speed at which it can be done. It may not seem like much because we're talking quite literally in nanoseconds, the differences between those.
Thank you.
No problem. Any other questions with regards to the 3 levels of cache memory?
Sorry, Mr. Kelly. What's
No
the purpose of these caches? L1, L2, L3, and L4. It's,
Okay.
Sorry.
Well, think of, I think I explained it a little bit. Think of it kind of like your websites that you go to on a day-to-day basis. Like if you're going to Google on a regular basis, when you load up that Google homepage before you search for everything, you don't want to wait for Google to send you that entire web page every single time you load it. It's not efficient. So your computer will keep a cache memory of that website. So when you request Google, the computer goes, okay, well, here's 99% of it so that it can be built. And all they need to send you is like the new advertisement and, maybe a couple pieces that have changed. So your cache memory will hold on to that and then give it to you so you can load that web page really fast. And if you've ever, when you're doing maintenance on your computer, if you've ever deleted your cache memory, the next few times you go to websites, it takes a lot longer for those websites to load because that's to download all that information again. Similarly, in your computer's making the central processing unit, all it does is making computations constantly. That's how you're able to see the graphics, how you're able to see everything. It's turning those ones into zeros into something useful for us. So it's a long series of very complex mathematical problems it's doing. And in order to do that, if we keep asking for the same thing over and over and over and over again, like if I was saying, 537 times 256, instead of it making that calculation every single time, it just tells the cache memory here, hold this for me because I know they're going to ask for it again. And I don't have to process it again. And they go, okay, well, can you please tell me the answer to that math problem again? I can just go grab it and say, okay, here it is, rather than me actually going through the process of running those computations. Does that make sense?
Mhm.
Okay. Yes, Humberto.
Yes, is this caching of the Google page similar to cookies?
No, different thing. Cookies are essentially little programs that are meant to track what you do. What do you look at? Where do you go? When you leave their website, do you go to a competitor and look for the same thing? That's what cookies are. They are to essentially keep tabs on you for the company so they can better advertise to you and know more about you. So two different things. Yes, Jimmy.
I want to get an idea of how many tasks can these 3 cache levels store at once, like roughly.
Roughly?
Yeah, just kind of an idea, because so many things are going on inside a computer. It's crazy.
Yeah. Yeah. I would actually need to look that one up for you, Jimmy. So
Okay.
I might have to consult with Google.
Yeah, I was just wondering as to the scale of this, because there's so many things.
Yeah, but it's just, it is a very, very small amount. Like it may be like a level 1 cache may only be like 15 bits or or 20 bytes or something like that, and then level 2 would be like 30 bytes, and then level 3 would be like 60 bytes. So it may be something along those lines, but just understand that level 1 is a very, very small cache memory. It's just for quick reference and things like that. Okay. Level 2 would be a little bit bigger, can handle a little bit more information. They're not going to ask you the scale of it. If it's a educational pursuit where you're just kind of like, I got to know the numbers. I'm one of those people that I like to know as much as I can about it.
Yeah,
we could probably find that out, but I would definitely have to consult Google to not give you bad info.
Okay.
Who's asking here? What do we got? Yes, Kaylin, I will do one more quick summary of level 1, 2, and 3 cache, but I will ask some assistance from the studio audience as well. Yes, the level 1 TJ level 1 cache is built into the core. So if you have 4 cores, so here we go. Who am I gonna let in? Hold on 1 second. All right, here we go. All right, let me just one more time. Let me go ahead and pause this here real quick. All right, here's kind of a breakdown of what we were just talking about. The level 1s and level 2s. So essentially, it has to do a lot of computations. It's trying to hold on to those ones that it's doing repetitively as much as possible to increase performance as much as we pretty much can. And that's where the level 1, level 2, and level 3 caches come into play. Now, we also have the IMC, which is included in the package as well. It's the integrated memory controller. It allows for much faster control of things like the L3 cache, sharing it among the multiple cores, and increase in performance. Like we said earlier, it is kind of like a traffic cop where it's pointing everybody in the directions they need to go, pushing the information where it needs to be, and helping share the load as much as possible to get as much efficiency as it can. So here we go. Here is a graphical representation of the L1, L2, and L3 cache that is drawn out much nicer than I did myself. So you can kind of see it where you have each of the 4 cores. You have the memory controller here, which tells where each of those, the information needs to go. And it is broken out into your 4 cores.
I'm glad you used the traffic cop analogy, because that makes the best sense, Kelly, to understand how your processor is trying to be as efficient as possible to move all the information around in the right way to be as high on that performance as possible. This should look a little better too for you, TJ, how it's broken down. So you get to see how everything looks. But also something that I'm pretty sure Kelly would say, if you guys look at the picture on the right, Go up to the sides for the L1 for me, sir. You see 32 KB for L1, which is data. L1, 32 KB there. And then if you go down, look how it got bigger. It went from 32. Now you got a bigger chunk, which is 256. If you go down to L3, it's 15 megabytes, which is bigger than kilobytes. So it just told you how those chunks go smaller as it goes
So
up.
was it Luis? Was that you asking about this? Who was asking about how much they could hold?
That was me.
Jimmy. There you go. Here's your answer.
Yeah.
For this particular i7 core, here you go.
Right.
Here's your answer as far as how much information it can store for the processor.
And it's 1,000 kilobytes to a megabyte.
Yes.
Yes.
Roughly.
Yes.
Roughly.
Yeah, roughly,
yes.
right. 10,
I
20.
got bigger quick.
Mm-hmm.
So that byte is a lot bigger on the bottom, but then once it becomes more known how to break it down efficiently, it gets smaller and smaller. Kind of like if you're making a cake and you're sifting the flour through the sifter. Like we got to get the big chunks out of the way, and then it gets smaller, more fine. And this is happening at such a lightning speed. It's not even something that we could probably fathom if we think about it, but that's what's happening.
Yeah.
It's getting smaller, more refined, and then it's pushing it out and performing those computations, those instances at such a crazy pace. I'm glad they put that in there because Kelly, I know you'll attempt it with your digitizer, but it does look a lot better.
It's a lot cleaner. I will give it that. I'll concede that fact. All right. Security.
Yeah.
For your CPUs, you have the EDB or execute disable bit. It's built into the processor, referred to as an XD in Intel or an NX in AMD. It is a function where if you send a signal to it to initiate that process, it will disable that processor. You can utilize this on phones to brick phones and stuff like that. So there is a code on the back of your phone typically. That's a good thing to write down. So if somebody steals your phone, they won't get to use it or sell it. They just brick the phone and it's unusable, unrecoverable. It can work with the operating system to designate an area of memory for holding your data and instructions. And then also requires compatible operating systems to be able to function. And it can be used with both BIOS and UEFI, so it is backwards compatible to the BIOS. Right. And though it is pretty good for stopping malware, it is not an end-all be-all. It's not something you should rely upon. You still need software to work for protection. In security, as we will move towards that, you'll get a better understanding. Security tends to be a balance between being secure and being convenient. The more secure something is, the less convenient it tends to be. And in your approaches to security, you are going to be taking a multi-layered approach. You're not going to be reliant upon a silver bullet to protect everything. There is no such thing. You want to set up multiple layers to make your system less attractive to hackers and things like that. It's kind of like your house. You can't make your house Fort Knox, but you can make your house less desirable than your neighbor for somebody to break into. So if they come to your house, they can't see inside, they hear dogs barking, and you have an alarm sign in front, they're going to be less inclined than if your neighbor always leaves their front door open when they go to your groceries, and windows are always open, and you know, they don't really care who comes and goes. So it's levels of security, and there is no perfect scenario, but you just try to make yourself less attractive to nefarious actors, so to speak.
There you go.
All right. Virtualization and integrated graphics. So modern processors can use software to create multiple virtual instances like virtual desktops, or if you want to basically have multiple operating systems on your system, on your computer, or if you're wanting to run tests or do sandbox tests and things like that, you can set up a virtual instance. Like if I'm operating off of Windows 10, but I have programs that only work in Windows Windows XP, I can create a virtual Windows XP system to run. I need to have at least one core available, enough memory and storage and stuff to be able to do that. But then I can create that instance and run it virtually on my system. But the processors that I have to be capable of doing so. They have to be compatible with that. So, and many times you will need to go into your BIOS or UEFI to turn that function on. It may not be turned on automatically. Oh, there, I believe we have a lab that you have to go in to the BIOS and turn on the multi-core functionality to get that to be turned on to create the virtual computer inside. It's either inside Test Out or it's in Coursera. I can't remember which one it is. The labs are blending together there, Marvin.
Yeah, it is. It's there though.
Yeah, there's one in Coursera too.
Okay. Thank you, Mark. All right, integrated graphics. Processors might include an integrated GPU or graphics processing unit to help manipulate graphics data, though it may not be sufficient to what you're trying to do if you're getting into gaming and stuff like that, but it'll be sufficient for your average user for anything that they may be doing on the computer. You might add a video card, as we were just saying. The motherboard may have one embedded, but those tend to not be very good. So the CPU would have probably the next level up. And then if that's not sufficient for what you want to do, you add a graphics card on top of it. Questions so far? Yes, Humberto.
Yes, if you have the GPU integrated and you want to upgrade your graphics by an extension card, what will happen?
Good question.
Well, you would need to verify in the BIOS that you're upgrading your GPU as to what it is so that it would know to go there. But typically what will happen is for normal everyday usage, it would use your integrated GPU. But then if you turned on a program that is very graphics heavy, then it's going to switch over to your graphics processing unit. And that's one way to actually diagnose if you have a power problem with or a problem with your GPU. If you're running, if it's good for day-to-day usage, and then you turn on a game and all of a sudden it just crashes, like, you know, you get a black screen or something like that, it's likely a scenario where your GPU is not getting the power it needs, or the GPU itself is failing. But you turn off the game, and you're fine. You can run for normal usage. So that's kind of how it works.
And also, if you think about it, Humberto, when you upgrade your graphics card, tell me about that process. What do you have to do? We know we put it in there. We got it in there. What are you doing in the back of that desktop that forces it to work with something? What are you doing?
On the back of whom?
On the back of the computer. You put the card in, you lock it back up. It's time to turn it on to see if you did it right. What do you have to do? How are you able to get what you just did to your monitor? You got to plug a cable into the new graphics card, right?
Yes.
So it's gonna be going away from the integrated graphics card, right? So that's another way that it's gonna force it. And if it's not done correctly, you'll get that black screen that Kelly just talked about. But if it's done right, it's gonna work off that, and you can always go back to your integrated one.
All right. Any questions so far?
Yeah, I got something. I found something interesting. I did it a long time ago. I learned how to sort of fix that issue. Whenever I face that problem, I go to my NVIDIA settings in the control panel, and then there is an option where it's like programs, and you click the program where you see there's a problem and there's a lot of lag and the screen goes black. What you have to do is that you have to configure the settings to your graphics card, because sometimes it just uses the regular normal graphics card that is not strong enough to handle it. So you change it to like if you have an RTX or something like that, and then you apply it, and then it fixes the issue.
Okay. But if you've applied the settings and it still goes black,
It must be a problem with the integrated
GPU.
graphics or something.
Yeah. So either it's
GPU.
not getting the power it needs, or the graphic card itself is going bad. So, but yeah, I like it. Next, CPU sockets. So we talked about past few days. We know who these manufacturers are. Let's see here. Kaylin, what manufacturer makes this one here? Who makes that one?
Is it Intel?
Do we agree?
No.
Okay. It's a 50-50
AMD.
call. It is AMD. It is AMD. Why do we know it's AMD?
Depends.
Pins.
Depends.
Yes, you got the pins sticking up here. Now, on modern processors, these pins that are sticking up can be about the diameter of a human hair. They are very, very small, very fragile. So you have to be extremely careful when handling a CPU, pulling it out of its casing and then placing it into the CPU socket. So you do need to be careful about that. But good try on that one, Kayla.
I hope did you guys catch my little thing that I did yesterday with Intel versus PGA? Did anybody catch that? If so, let's speak on it, because I felt this is how I held on to it, because it took me a minute to try to hold on. You got to make it your own. So how would I remember LGA is for a certain brand? It's because, anybody remember? Because if you do, I want you to say it. I don't want to have to say it again. Man, I be working the chat. I need you guys to be in on that chat. I promise you, I'll be throwing nuggets out there, gems. Intel L, LGA, Intel GA. That L lets me know that it's Intel. Intel is LGA. That's how and once I lock Intel down, once I lock LGA down, then PGA had to be AMD. So you caught that? That's what I'm, Jimmy. Like I do it for you. I promise you, I do it for you. Like I even write it. You say you wrote it down, Ms. Diaz? Intel GA. That really just solves that whole problem of trying to figure out who's AMD, what's PGA, what's LGA. So that was my thing. You know, everybody has their own way. So, but that was my way. Go for it, Kevin.
All right. So LGA, or land grid array. So it's like the land, it's very flat. So you got to remember that. LGA, land grid array. And this is with regards to the chip, not the socket. So land grid array, smooth, very flat. Pin grid array, it has pins. AMD has pins. Intel GA, as Marvin put it. So it's very flat land. I mean, I'm incorporating it, man. I'm working it in.
You got it, man.
And below we have it, the socket already inserted, and they even have a dollop, which is probably going to be too much, of thermal paste applied. So what it would look like after it is already installed. All right. Here is a layout of the socket types that they would have on motherboards. Again, we don't need to memorize all this, but we need to understand the naming style. Intel is land grid array. We know that because it's smooth. All of their sockets typically start with LGA because they are LGA sockets. Even this one is FC LGA. So all the Intel sockets start with LGA. So if I have an AMD chip and they're giving you Intel sockets, which it starts with an LGA, you know it is non-compatible, it will not work. So for the exam, you probably will get 1, maybe 2 questions on this. Understand the naming styles. What are the different families of chips? Celeron, i5, things like that. And then understand which companies name their, what they name their sockets. Intel, AMD, or starts with LGA.
Exactly, Louise. That's exactly right. So they have a way to differentiate, but what Kelly is saying is watch the naming, because the naming helps support what that question could be asking, and you can get rid of answers just like that, because how
you will get down to 50-50 at minimum, just knowing the different naming styles. So here's a look at the Intel sockets. You can see all the pins sticking up. And then they have these coverings that will come down, and then these clips will lock the chip in place. It's called a ZIF or ZIF for zero insertion force. All right, AMD. Think of it like radio, AM, FM. So the AMD, their socket types tend to start with FM or AM. So if they give you an i5 processor and they give you a bunch of FM1, FM2, AM3 slots, and then they give you a LGA 1437, which one are we pairing it up with? Because remember, AMD sockets cannot accept Intel chips. All right, here's a look at some of the AMD sockets. As you can see, it's a bunch of pinholes where the pins from the bottom of the chip will go down into it and then connect with the connectors at the bottom of that. And they also have coverings that will lock these in place and insert them.
Kelly, if I can let you take a quick breather.
Yeah, go for it.
If you notice FM1, FM2 versus AM3 plus, what do you see on FM1 and FM2 that you don't see on AM3? Very obvious.
That hole in the middle.
There you go. There you go. PK, if I told you that AM3 plus had more pins, more holes, what would that suggest to you? Just what could that do for me?
Process faster. I don't know.
Man, TK kill it. Without don't. That's it. You just said it. The more pins, the more connections of that CPU to that motherboard allows for more processing possibility. If Kelly go back to that slide right before, you'll see. Okay, I'm about to grab it. That's Chris, Kelly. The bottom ones have more holes. Just wanted to say that. I'll be right back.
No problem. So yes, so all these ones with the little pin holes, these are all AMD sockets. The pins will fit down in them. Just a reminder. And then if we go back to the Intel, you can see all the pins sticking up from the sockets that the flat chip would sit on top of each of those pins to make those connections. So, and then we have Intel has the LGA naming style. AMD has the AM FM style. So AM and AMD, AM FM. Any questions so far? All right. Move right into it. Managing CPU heat. Most of your issues that arise from your CPU are usually coming from not enough or too much heat causing issues. Managing this means you're going to need to check your heat sink, make sure it's not covered in dust. If it's covered in dust, it's not going to be able to disperse the heat properly. If your fans are clogged with dust, they're not going to be able to push the air through those heat sinks to help disperse that heat properly. And critically, if you did not apply thermal paste to your CPU, that heat sink is not going to be able to draw that heat out in an effective manner to be able to move it away from the central processing unit in a safe manner. CPUs can get so hot if you just like open it up, and if it's heated up at that moment and blow on it, you can crack the CPU at that point, just blowing on it, because that cools it enough where it will crack it. So you need an efficient way of moving it away, and the thermal paste provides that medium so it can transfer it to the heat sinks to disperse it. Heat sinks are what are considered passive cooling, means nothing extra needs to be done. Like on the North Bridge, all you see is a heat sink sitting on top of it, and it's just slowly pulling that heat away, and then the air moving through it is going to disperse it. The CPU needs a little more help than that, so typically we add a fan to the mix. So the fan is forcing air through that heat sink to try to disperse that heat a little bit faster. Typically, when you purchase a computer, the standard cooling method will be heat sink and CPU fan. There are other methods, though. As we just talked about, that heat sink in the middle right there, that is a passive cooling method. That is just a heat sink by itself. Typically, you will see that on the North Bridge alone. And then you have case fans that will move the air through the computer. And then you have a heat sink fan right here at the top that can be secured on top of heat sink and the air force through it. This is the most standard method for cooling a central processing unit. For those who want to get a little fancier, or you're using a much higher end processor that needs more effective cooling, we have the submersible system, where you have the entire board itself submerged in a special mineral oil. It is non-conductive, and it is one of the most effective ways for actually dispersing the heat from a board. Unfortunately, it is very expensive to set up, and it does require maintenance. It does look cool, I'll give it that, but for very high-end computing, they may do something along these lines, just because it is one of the most effective ways to remove heat from the processors as they work. One of the more common ones that you will see outside of your standard would be your liquid cooling. Inside the computer, they will have this liquid cooling that is attached to a radiator, kind of like in your car, and that radiator is attached to the CPU with the thermal paste itself, and then it will continually pump that liquid through the radiator, allowing it to cool. And you'll see on modern gaming systems, they'll use different colored liquids so that the aesthetics of it, and they'll use the clear tube so that it matches what aesthetic they're going. If they're going for like a purple color system, or yellow or black or blue, they do all different kinds of stuff to make it look really cool, and LED lights and stuff in there. But the liquid cooling is much more effective at drawing the heat away than just a standard heat sink and fan. Not quite as effective as a submersible system, but significantly less in cost and maintenance for that end. Are there any questions so far with the various cooling methods we can use? Does anybody have a liquid cooling system on their computer? No?
Is your hand up, Kelly?
No, I don't have a liquid cooling system.
I was about to say, I didn't think you did, because I'm like, you're Mac heavy, and I don't see many Mac systems
No. Well, I
No.
mean, the PC that I'm gonna build, yeah, it's gonna require a liquid cooling system,
Okay.
but I'm not there yet. Not there yet. One step at a time. But yeah, that one's gonna require liquid cooling. All right.
Go for it, Rienzi.
I was just wondering how would we know if we have that? 'Cause
Oh, you'll know.
Oh, you would know if you had liquid
is that
cooling.
like on the outside?
No.
Oh, okay.
But the liquid cooling is going to require some maintenance, and on any state, like I'd say about 80 to 90% of computers have just the standard heat sink and fan.
And a lot of people who are like into that world, if you have liquid cooling, you want to show it off. So you'll have a case that's clear.
Yeah,
You have some
clear.
RGBs. You'll have some colors. Like you really want to show it off. You typically won't keep it closed. So that's another reason. And it's kind of for that gaming community or the high end graphic heavy community, because that cooling is a must. Like Kelly just saying, Kelly won't be. Well, Kelly, you say you might do some gaming, but he may have other interests that requires more computing power, which will require better cooling options, and that's going to be the best bet.
So you can see, you know, they have multiple fans that they'll install in these. A lot of them have the clear sided cases. You know, if we look at this right here, you can see these tubes running through it for cooling. I mean, there's a lot that could be done with it. They become almost like display pieces, or you know, not just a computer. It's also kind of a piece of art that someone is showing off on their, you know, on their computers. Yeah, they want people to kind of come in and go, oh man, that is cool looking, you know. So, you know, they take a lot of effort into make them look as cool as possible. They take a lot of effort in their cable management so that they don't just have a bundle of wires in there. All of them are nice and lined up, and it just makes it a very, very nice display piece. I wonder if they have any of the open air PCs.
Yeah, they look like a fish tank almost, like with all the cool lights and stuff.
Yeah. You know, so, you know, they'll have some that are like, let's see if the open air ones, they had some really cool ones that were like built onto the wall. Like they're actually on the wall, like a display piece. And they have different themes. Like one guy did one that was like a Transformers theme. So he had like, you know, all the PC exposed and stuff like that. And it looked like Bumblebee, like a part of Bumblebee's armor or something like that. And he had like all the liquid cooling was yellow. And so the whole color coordination was all yellow and black and stuff. Like people put a lot of work and effort into this stuff. Yeah. And it's, you know, it's kind of neat when you see what some people do. And there are,
Fidel said in the chat that it's too risky, Kelly. I just want to say you'll do some tests before you actually this is something you do well before you kind of get it all fully buttoned up, but you'll make sure that you have it fully enclosed before you allow it freely flowing inside your PC.
Well, the liquid cooling allows you to be able to do some of that open air stuff.
Sure. Yeah.
And so that's where a lot of those modifications are going to be in place. So, but yeah, cost on this price range can vary. Your mileage will vary drastically. I mean, if you look up on YouTube, there's some guys that do a lot of custom builds and stuff like that. There was one guy who did a desk PC where it was built into the desk and it had a clear acrylic top where you could see down into it and all the stuff that was on there. That was like a $60,000 computer that this person built. So, I mean, they can go from, you know, a couple $100, you know, getting, you know, starting to get into it up to tens of thousands of dollars, depending on how much money you want to throw at it. So absolutely mileage will vary. And also if you have somebody else build it versus you doing it yourself makes a pretty big shift in the price as well.
Of course.
$60,000.
Yep, for a computer.
But if you guys are like interested, there is a site, I'm posting it. It's a guy named Bitwit that he actually he rate people's PCs like that, and he gets millions of views by people sending pictures to him, and like Kelly saying, they have it set up like art, and he goes through and talk about, hey, that's really nice how they did this, how they did that. I would have did this, but as you see, they put a lot of effort into it. I find myself watching them just because I'm like, dang, I'm not that creative to think that way, but yeah, if you're into that type of thing,
Well, think about it like for upgrades on your car, like you can get a base model car, you get you from A to B, has a basic stereo, does what you need it to do, doesn't cost very much. But then you can take that same basic car and apply a whole bunch of upgrades to that car, upgrade the paint, add lights, better speakers, better music, turbochargers, all that fun stuff to it. And you're going to like almost triple the cost of that vehicle, but it almost becomes like a piece of art at that point on top of just being a car. So
for sure. It's almost the same. You're right, Kelly.
It's just like a community, that surrounds that kind of stuff. So
I agree.
All right. Removing a CPU and installing it. I know it seems like we're going over this stuff repeatedly, but it is good to kind of help drive this stuff home in our memories. A lot of these steps may seem the same, but as with safety, you don't just talk about it one time and move on. You kind of keep reiterating these things so it becomes like muscle memory. What's the first thing you do before you work on a computer? Power it down, hold it for 5 seconds to disperse the charge, and unplug it.
Yeah,
that's what we do. So steps for, removing and installing a CPU, keep the new processor in its protective bag, in its case until the very last second. Don't pull it out and look at it. It's pretty, it's shiny, it's all nice and fancy. You want to get it out and look at it, but you run the risk of dropping it and damaging it in those processes. Keep them in place until you are ready to install them. Power down the system, press it for 35 seconds before you unplug it. Open up that side panel, get ready to access the internal parts of the computer. Slap on that ESD bracelet or mat or gloves, whatever you have handy. Then you should have pretty easy access to the CPU right there. It is pretty open and exposed. You would want to remove the heat sink first. It will likely either be held in, the fan will likely be either held in by clips or screws. So you need to undo the clips or undo the screws to get the heat sink off. Take extra care when you're unscrewing it using the X method like we talked about yesterday. So you do like upper right, bottom left, upper left, bottom right in that order to undo it so that you don't bend or crack the processor that you're pulling out. And then you would remove the heat sink if it is sticking. Marvin gave us that wonderful technique using dental floss to kind of, use it kind of like a wire cutter to kind of pull through and just break that seal on the thermal paste to go ahead and remove it. And then you verify the condition of the thermal paste. Is it still in good condition where you can still use it on the bottom of the heatsink? If it isn't, you're going to reapply more when you reinsert. Now you got everything exposed, you're ready to remove it. CPU sockets tend to have a latch or an arm that holds that CPU down firmly onto the socket. You want to make sure you undo that to release it, open up that cage, and then you open up the socket, pushing down gently, and then it should release to fully open. Now, how am I going to get that CPU out of there? Just reach in and grab it, pull it out.
It's like a tool that we have. It looks like I forgot the name of it, but it looks like a clip type of thing. It's like I forgot the name of it, but you use it for safety. Like you remember the story that you told us when the T-8 grabbed it with his hands and it fell off. That's why you use that tool, so that doesn't happen.
Okay.
But I
like it.
forgot the name. So
All right. The name of that tool is called a chip extractor. So I would highly recommend it. I've seen techs just use their hands repeatedly, but I've also seen the result of not using the chip extractor and what that can cause. A whole lot of lost time and or a whole lot of lost money. So chip extractor, pull it out. Good to go. Double verify, especially if it is an AMD and you are going to be reusing that socket. Turn that chip over and make sure all the pins are still there. None of them have broken off down into the socket. It does happen. Very rare occasions where those pins can get stuck and then kind of snap off as you're pulling them out. So you just verify, make sure they're all still there. Otherwise, you're going to have to take a little extra time to get those the pins extracted from the socket with some very, very fine tip tweezers. All right. So right here, perfect picture of what not to do. There you go, grabbing it with your fingers. So take extra care, hold it by the edges to make sure the pins are not bent. And then you take the processor that you're removing, put it in an ESD bag just to make sure it does not get damaged. And you may end up wanting to use this processor for another computer, like you may be upgrading your higher end computers, but taking your the chips that were in those and moving them down to the next tier of computer below that. So you want to reuse and recycle these parts as much as we can to save cost where we can. Because contrary to popular belief, when you were in IT, they are not going to give you an unlimited budget to upgrade everything. You're going to have to reuse and get as much life out of a lot of the components you have. So you remove the CPU, the new CPU at this point, the nice, bright, shiny from its bag, being careful of the edges, lifting it up with that chip extractor, and carefully align that fun little triangle, which indicates what? Aijan, what does that triangle mean?
That triangle means one pin.
There you go. That is the location for pin 1, and we match that up with the triangle on the board. You should be able to see it pretty readily here. See, right here is the triangle on the board to indicate to you, you match up the triangle on the pin and the triangle on the board so that you know the orientation of the chip when it is being placed into the socket. You can even see it over here. Here's the triangle. There's the triangle, nicely matched up so that the chip is as it should be. Questions so far? All right. Now that we've got the brand new fancy chip installed, we're going to close that nice little covering over it. Take the locking arm, put that down and lock it into place so it is nice and secure in place. If it is not going down easy, do not force it. You will either bend or break pins if that is the case. That means it is not sitting properly in there if you have to push hard. It should very easily fold into place and then the locking arm will apply the additional pressure needed. After we have done that, we will add our thermal paste or thermal compound onto it. If we are reusing a heatsink, we have a brand new heatsink, it should already be applied, and just have to remove the covering for that thermal paste before we apply our cooling medium, whether it be a heatsink or a liquid cooling setup or what have you. After that's done, we place the fan on top of the heatsink and screw it back down or clip it back into place as it should be. Then we can connect the fan back to the motherboard, connect the power supply back to the CPU, replace the door on the side of the computer, and then plug and pray. Plug it back into the wall, turn it on, hope you get past the post. Once you get past post, you can verify everything through the BIOS, make sure all is seeing what it needs to see and is able to function. Questions so far?
you can barely see the heat sink because the fan is covering it.
Yeah, because the fan sits right on top of the heatsink. Absolutely.
That's thermal paste and heat sink are the same thing, right?
No, no.
No.
So the thermal paste is this little goop. It's like the consistency of toothpaste. It's right here. So it's this little dollop of like what looks like toothpaste that gets put onto the heatsink or gets put onto the CPU. And then you put the heatsink on there, which the heatsink is like it's like a flat piece of metal with a bunch of little spikes sticking up on it. Looks like this right here. Does that make sense? So the thermal paste sits in between the CPU and the heatsink. And then, so you have CPU on the bottom, a little bit of thermal paste, heatsink on top of that. And then you put a fan on top of the heatsink to blow air down and through the heatsink to disperse the heat.
How do you make sure the fan doesn't fall off of the heat sink?
How do you make sure the fan doesn't fall off?
Yeah.
It has, they typically have 4 screws that will bolt it down or clips that will lock it into place.
And it's not uncommon to have, they could be mated together out the gate, like just one piece.
I have seen that. And Janina, yes, if you have too much thermal paste, it can like spread out and go down and damage components and stuff like that. So if that happens, you do need to kind of clean it up before you go any further. Like if you apply too much, yeah, you got to clean up the excess to make sure you don't damage components long term.
Question. So you don't spread the thermal paste, you just kind of put that eraser size down, and so you don't spread it across, and then just set the heatsink on top.
Correct.
Gotcha.
I mean, you could, but don't really need to. And then like on the modern components, it's already perfectly proportioned and spread out for you.
If you put it right there in the middle, when you made it, it spreads out evenly across that processor ponder. So it does that job for you. You trying to evenly coat it, it's not a peanut butter sandwich, but most of that is going to spread out perfectly the amount that it needs to cover that process. So it happens through that mating process.
Okay, thank you guys.
No problem.
All right. Let me stop, share sound. Of course, there's all my stuff out of the way. All right, got a quick video.
Hi there, this is Ranjit from tech2bus.com, and in this video we're going to install Intel processor on this motherboard. And the motherboard that you're seeing is an OSIS motherboard based on the Intel Z77 chipset. And this supports both the Sandy Bridge and the Ivy Bridge chips based on the LGA socket 1155. And I'm going to use a LGA 1155 chip on the same. And the general thing before attempting to do something like this is that you notice this is the motherboard. And the thing that you have to keep in mind is any static electricity that you might have built up should be dissipated before even you touch the motherboard, because it can damage the motherboard. So I suggest wearing a anti-static wristband or grounding yourself before attempting to do the same. And for this test, let me move the motherboard. I'm using a stock Intel kit in which we get this CPU cooler and the chip itself. And if you take out the CPU cooler, as you see, the thermal paste is already pre-applied. So I'm not going to apply the thermal paste here. But if you're using an aftermarket air cooler or something like that, you might need to apply the thermal paste on the chip. And this is the actual motherboard. Let me just zoom in a little bit, because this is the area where we're going to work. And the first thing you do is gently press this and move this and open this latch, and this latch will open this way. And now you need to open the processor that you have. Do notice that this is the processor and you should not touch this area. Gently lift it, and let me just move the motherboard, and let me show you one more thing that is a little bit important. Let me see. Yeah, if you notice here, you can see these two notches, and on the socket of the motherboard also you'll have similar two notches. Let me break the motherboard now, and as you can see, here are the two notches. So, and we also have an arrow over here, and we have an arrow on this. So you just gently place the chip and it should sit down. And now what you have to do is bring back this plate like this and depress the lever. Do note that you might have to apply a little bit of pressure. That is okay. Now you have installed the chip. Now what you have to do is, now we are going to install this fan on the same, and to do that it's also pretty easy. Let me show you the motherboard actually. Let me just zoom out a little bit. And if you notice, we have these 4 holes over here, and our stock Intel cooler will mount there. And let me just zoom in a bit so you get a better view. And what we do is we gently place this over here, over the 4 holes approximately, and those 4 pins should just go down gently. And now what we do is hold on to the processor like this and just depress, and you'll get a clicking sound. And do the same for the next one and proceed with the others. You should get this clicking sound that you have heard. That means we have fixed the CPU cooler. And now the last thing that we need to do is, let me show you the same. Your motherboard should have a header like this known as the CPU fan, and you now just need to attach the CPU fan and that's it. And that's how you have installed your CPU on your motherboard. And let me just turn the motherboard 1 second. And if you look at the back, I want to show these tiny pins. They should come out. That means you have successfully properly installed the stock Intel CPU cooler. So that's how you actually install Intel CPU on a motherboard. And in my next video, I'll be installing the other components like RAM, connecting the actual SMPS to this motherboard, and we're going to power it on. So stay tuned to my YouTube channel for that. If you aren't subscribed, hit the subscribe button. If you found this video helpful, I'll appreciate if you click on the like button again below. That's it for now. This is Ranjit from tech2buzz.com, and I hope to see you in my next video.
All right, gives a pretty good close-up view and representation of installing it. A few caveats with it, but for the most part, great install setup, things like that. Any questions so far? That particular one had the heatsink and the fan already married up, like Marvin was talking about. So they were already put together, and then you are putting them on the CPU as a single unit. All right. Some pitfalls you may run into in the install of a new chip. Like we were stating, on the pin grid array, you might get a old pin stuck in the socket, break off. Now, you should try to prevent that from happening using balanced force to kind of lift it up. If a pin does break off, you should be able to use fine tip tweezers to be able to go in and pull the old pins out to clear the path so that a new chip can be installed. Thermal paste has fused the CPU and the heat sink together. Well, we talked about this either. As well, you can keep the CPU locked in, and then you can either slowly twist. If a gentle twist does not free it up, dental floss. Dental floss will help you most of the time. Or you can go straight to the dental floss if you don't want to run the risk of twisting the chip. The arm won't latch. If the arm won't go all the way down, there is a possibility that the chip is not seated properly. So you might need to come out and verify that the chip is seated right, and you are good to go at that point. So a moderate amount of effort may be needed to push the arm down, but you should not be having to bear down on it to make it lock into place. CPUs rarely run into actual mechanical problems, aside from an actual default from the manufacturer themselves. And if that is the fact, it typically is catastrophic and it won't work as well. Most of the issues tend to do with overheating. So it may be an issue of the heat sink malfunctioning. The fan may not be working properly. The motherboard may also not be maintaining a constant flow of power to the actual CPU itself. So it may be a motherboard problem if you're having intermittent issues where it's crashing. And then also that may create intermittent communication issues. Catastrophic issues would cause the system not to boot, which you would hear the series of beeps from the post error, and then you would look that up on Google to see what the actual post error is, to see if you can remedy that problem. Any questions with regards to CPUs? Are we CPU experts? Ready for the exam today? All right. Well, from this technical session, we should be able to describe various types of processors and articulate how to select a processor to match up to our system needs. You should be able to identify a CPU as a central processing unit and explain its purpose and requirements to keep it functioning. Choosing the appropriate cooling method depending on what your needs are and what you're trying to do. And then the steps for installing and removing a processor as well as a few symptoms of troubleshooting that may need to take place if you're having cooling issues or somewhat for the processor, and then addressing them. With that, we will stop the recording.